they're implemented in our Mesa driver. When we run our Mesa EGL driver, we can create all these EGL images from different OpenGL resources. You can bind to a texture, we can bind it to a render buffer. If you're running Gallium, you can find that the Gallium drivers actually have an OpenVG implementation. The UI drivers only support OGL and GLES 1 and 2. But the image extension is available. And one of the interesting things that I've done on top of the image functionality is integrated with kernel mode set. We came up with an extension in Mesa that lets you create an image, EGL image from nothing basically. Typically, you create an EGL image from one of these resources in a client API, take a render buffer, create an image. But this extension lets you allocate an image, and which is basically allocated from not from an existing resource, but just directly from the memory mapping. And when you allocate it, you can specify a few hints, like you want to use it for scan out, or you can say that you want to share it with a different process. And the extension lets you access some of the gem details of the object, so you can ask the extension to get the object name for the underlying gem buffer. You can pass that object name to a different process, which can again create an EGL image from that buffer. So now we have two processes sharing an EGL image based on the same buffer object. So we can pass buffers around. And the other thing is we can ask for the gem entity, the in process identifier we use to reference the buffers, which is also the ID that we use to return most of it. So we can create the image, we can say we want to use it for scan out, then we can bind it into the OpenGL object, render to it as a render buffer with an FTO, for example. And once we've done that, we can go back, take a look at the EGL image, and we can get that in, create a KMS kernel mode setting frame buffer object, and then tell kernel mode setting, please scan out from this image. So once we put the pieces together, we have the option to run EGL on the frame buffer directly. So this doesn't use X, this doesn't require any Windows system. It lets you allocate a scan out buffer, render to it with accelerated OpenGL, and then use it for just data mode, or use it with page script. So you can have two images around, you render to one, page script to that, then once you have page script, you render to the other, and then page script to that. So you can do double buffering, or you can do triple buffering if you want to do that. So it's basically up to the application to allocate a set of EGL images, render to them, maybe free them when it goes idle, and then use the KMS API to set the image you want to scan out from. And it works naturally because the KMS API works with multi-head. It works with, you can have one big frame buffer, you can have different scan out buffers per output. And all this is naturally supported with this because it's just a tiny little bit of integration with the two APIs. So you can allocate two different outputs and set them to two different modes, or two different outputs. Or you can allocate one big buffer and you can ask your two CFGCs to scan out from that same buffer and show the same image on two outputs. So it has all the features that Render has because we're just using the online KMS, but it's lets you integrate that with OpenGL. And so one thing, last thing I want to mention about EGL is that we're actually working on an official Kronos extension to let us share images between processes. So what we have in Mesa right now is Mesa direct specific extension that if you have DRM, you can allocate hands, you can talk to current node setting, and this works very well if you have a Mesa antenna-based system. But there's been a lot of interest in sharing images across processes. Mozilla, for example, they want this so that we can render a tab content in one process, and then in a different, the main window process, they can take that tab and pass it into the browser, so they can have out-of-process accelerated rendering of different tabs, and then integrate all that in one window by compositing the different EGL images in so the people from Australia take part. They're so interested in the feature, and or they used to in other companies that are part of the process. We're at this point that we actually have a final draft of the extension, and it's similar to what we have, except that there is some authentication around it, which is also part of the extension. So essentially, the process you want to share the image with has to generate a system-wide ID for the for that process, which then it has to, by IPC or some other means, have to communicate to that other process that I want to share the image. So if I want to share the image here with the process over here, I have its ID of its address basically, and I say share this image to this address, and then that gives me another unique system-wide unique ID that I can pass through IPC again to that process, which can then open that unique ID. And it's that the end result is the same as what we have with the DRM beta extension, that we end up with an EGL image that's based on the same underlying kernel model, but this doesn't actually involve any DRM API. This is a kernel extension without any beta kernel. So it's something that can be implemented by different EGL vendors in the EGL stack and in this facility as well. So last point, this is a short talk, but I just want to say about the GLES 1 and GLES 2, the embedded subsets, is they're also now available in Mesa. They've been available for Gallium drivers for a while, because with Gallium you can have different state trackers that interpret different APIs. So in the Gallium world, it's just another API alongside the OpenGL and OpenBG that already exist. So these are different state trackers that pass a different substance of the GL standard and talk to the Gallium language. But DRI drivers, there was no way to provide this API. We always only provide the full OpenGL API, and there are a few semantic differences. It's not a strict subset, and it's also nice if you're actually working on a GLES application that you can compile against GLES library instead of the full EGL library, so that'll catch if you use a GL simple or if you step outside the subset. So there's definitely benefit to having a real GLES2 library and implementation available. And that's now available in Mesa. What I did was I added the feature to the DRI interface to create a context for a specific API. So when you load a DRI driver, you need to see it has the existing code interfaces. But there's a new entry point that lets you say, when I create this context, I'm going to use it with an GLES 2 API or a GLES 1 or maybe full GLES OpenGL. So that way, the DRI driver can initialize the dispatch table and the entry point so that it checks the parameters accordingly to the ES2 spec. So we don't pass in enums that are not valid for ES2. We don't call entry points that are not valid. So all this allows the driver to initialize the entry point correctly, and then we have end-user libraries, GLES 1 and GLES 2.so that you link to. So and it's very similar to how full GL works, but we just need that feature to specify what API we're working with. And all this is available, and there's very cheap and specific code in this. Most of this is basically managing the Mesa dispatch tables and initializing the right API. And there's not much available that individual drivers need to do to provide much API support. The way I set it up is that if a driver doesn't do anything, then it doesn't advertise anything else than full OpenGL. But it's a fairly simple task of sitting down and looking at the drivers. Can it support the USM2 sharing language? Does it have the features that otherwise the USM that GLES 2 requires? And if all that's in place, you can set the bit, and then the DRI and EGL will do the rest, advertise the API and set it up correctly when the user asks for it. So it's fairly simple to enable this in the other drivers, but I only did it for Intel. And it came together pretty nicely with our sharing language compiler effort as well, because Ken was able to take that compiler and then go through and make sure that it supports the different subsets that GLES 2 uses. So it's actually a pretty good implementation now. We have the shading mechanism in place, the APIs in place, and we support quite a few of the EGL image extensions. So that's what I wanted to say here. I thought about maybe looking through